Hey there, my awesome algebra students. This is going to be our first recap that talks about the material that we've learned so far. We will have these after every little section of learning, every 2 to 3 weeks. And I'm going to try my best to keep it under 7 minutes, and we'll see how I do on this first one. So what we started out learning was that a constraint is something that limits what's possible or reasonable in a situation. So we have these quantities, right? I'm buying some food and pizza and snacks for a party, but I only have $50 to spend. That's a constraint. Or I can invite a maximum of 20 people. That's another constraint. A lot of you talked about budgets when you came up with your own examples. So then we got into, well, yeah, sometimes quantities can vary or change, and sometimes they can't. And so, for example, let's say we're going on a field trip to the museum, and the cost of admission is $18 per person, and the cost of renting a bus to get there is $180. So to get the total cost, I might say that 18 times P plus 180 is T. So P is the number of people, and T is the total cost. The number of people and the total cost are going to vary or change, and we can represent them with a variable. The number of people changes, and then the total cost changes. The cost of the bus is fixed, as long as we're just taking one bus. It doesn't change, and we can show these fixed quantities with a variable or a number. Maybe I didn't know that it costs $180, but I know it costs the same something, no matter how many people are going. So in that case, I'd use a variable. So then we got into looking for some patterns in tables and using those to write equations that describe the situation. So let's look at this one. A plane departed from New Orleans and is headed to San Diego. The table shows the distance from New Orleans, x, and its distance from San Diego at different points along the way. This should seem to you like that activity of distance from home and distance from school, where as we got closer to one, we got further from the other. But we talked about some different ways that we could write equations to represent this relationship here. And so I could, for example, start out by saying, I'm noticing that x plus y is equal to 1,600. Maybe I want to put that in terms of x or y first. So maybe I first want to say, okay, well then y is equal to 1,600 minus x, or x is equal to 1,600 minus y. So then we started talking about equations in one variable where we have one unknown quantity or quantity that can vary, and equations in two variables where we have two unknown quantities or quantities that can vary. So let's look at this first one, and you might be thinking, well, I see two variables there, but read through the prompt with me. So this equation 2L plus 2W equals 72 represents the relationship between the length L, the width W, and the perimeter. If we know one of those, so if we know the length is 15, we can rewrite this equation as this right here, and then we've got an equation in one variable. And in order to figure out, well, what is that W equal to, we're asking, well, what would be the value? Let me move this camera. What would be the value that I could replace W with and have that be a true statement or true equation? And so if I replace W with 21 and continued to simplify, I'd have 72 equals 72. And then we talked about, well, that's a little bit different in how we'd approach this equation in two variables. So let's say Tyler spends $45 on t-shirts and socks. A shirt is $10, socks are $2.50. So we have T representing shirts, P representing pairs of socks. And so we can represent this situation here with this equation in two variables. And so in this case, more than one pair of values for T and P can make the equation true. So Tyler could buy 3 shirts and 6 pair of socks, or 4 shirts and 2 pair of socks, or 2 shirts and 10 pair of socks. And in every single case, he'd end up spending $45. So finally, in this section, we talked about how we can use graphs to say something about a situation and its solutions. So let's say now we are buying beans and rice to feed a large gathering of people, and we have this constraint that we plan to spend $120. Beans are $2 a pound, rice is 50 cents a pound. So here's an equation that represents that situation there. 2 times x plus 50 cents times y equals 120. And now let's look at the graph. And so we talked about how all of the ordered pair that fall right on this line are true solutions to the equation because it satisfies that constraint of spending $120. So we can see here that we could buy 10 pounds of beans and 200 pounds of rice and spend $120. Or it looks like we could buy about 45 pounds of beans and then 60 pounds of rice and still spend that $120. These ones, the ones off the line, are not solutions because they do not satisfy that constraint. We could technically buy 20 pounds of beans and 80 pounds of rice, but added together, they wouldn't be $120. And so now you're all caught up with what we've talked about in lessons 1 through 5 of Unit 2.